Everybody, and today is our great pleasure to have Dr. Zhicheng speaking with us. So, Professor Jing got his undergraduate as well as a master's degree in Beijing University before he moved to Yale University for his PhD. And afterwards, he worked as a postdoc at the signature beam in Chicago, I think affiliated with university. And then he began as assistant professor at the Case Western Reserve. And now he has been working at the STAC for 3 years, as associate professor. So Professor Jing's previous work has mainly been focused on measuring the physical properties of silicon melts and later on the core melts. And in this talk, he's going to talk about the other type of melt, of this carbonate melt physical properties. So with that, I will give the rest of time to Professor Jing to talk about the research that published in 2020. And then please leave about 15 to 20 minutes for discussion with the audience. And meanwhile, we're also doing the recording since it is a published work, and we are going to post them on the YouTube as well as Bilibili. So some of the audience who are interested on this topic, if they miss a talk, they could still come back to watch the video. So with that, I'll give the time to Dr. Jing.
Okay, can you hear me?
Yes, please keep your video on so that is easier for audience to see your face while you're talking.
I think I'm on, no?
Yes, you are on, you're on. It is all good.
Yeah, okay. Thanks, Professor Zhang Zhou, for the invitation and also the nice introduction. So first, I would like to thank my collaborators, Man Xu, Julian Chantal, and James Van Orman at Case Western Reserve University, Suraj Baskin, Mainak Mukherjee at University of Florida, and Tony Yu and Yanbin Wang at the University of Chicago. So Man was the first author on our PNAS paper. He was my former PhD student and is now a postdoc at University of Chicago. And Julian Chantal was my former postdoc, and he's now at the University of Lille in France. So today I'm gonna talk about two things. So first, I'm going to give you a review about the experimental methods we use to determine the density and sound velocity for melts, and also some of our recent developments about the experimental techniques and some results. And next, I'm gonna talk about our recent results on the density of carbonate melts and related to the carbon-induced melting in the upper mantle. As we know, there are many liquids in the Earth and planetary interiors. For example, we know that the Earth, the outer core, is made of molten iron. Of course, there are some light elements alloyed with the iron. And because of that, seismic shear waves cannot propagate through the outer core, and also the motion of the iron liquids generates the Earth's intrinsic magnetic field. So the liquids inside Earth is quite important to many things. And another example would be we see volcanoes on the surface, so we know there are molten rocks inside Earth. And in fact, there might be melts in the deeper part of Earth, for example, in the upper mantle transition zone, and even in the lower mantle. And these melts are important for the chemical evolution of Earth because when you have some partial melts, incompatible elements would prefer to enter into melt and move along with the melt. So when you have some melt produced inside the Earth and circulate around inside, you would have a redistribution of chemical elements. Another example would be for the early Earth and other planets. there might be pervasive melting in the mantle, and these are called the magmotions. For example, this is the lunar magmotion, and the cooling of the magmotion determines the stratification of the lunar mantle and crust and formation of the lunar crust. So melts are very important. But what is a liquid in terms of physics? Okay, we know that for a solid material, and if you use modern techniques, for example, you use TEM or STM, you can actually see the crystalline structure of a solid. And inside the solid, the atoms are arranged periodically to form a lattice, crystalline lattice. Okay, and the atoms would vibrate around their equilibrium positions when there is temperature. But for a liquid, what happens is that with increasing temperature, the vibrations of atoms in a solid material becomes more violent, and at certain temperature, their kinetic energy would be high enough and comparable to their bonding energy of their chemical bonds, and at the end they would break the bonds and vibrate violently and become a chaotic structure. But it's not entirely chaotic. In fact, there is some certain short-range order in the liquid, but it lacks the long-range order in a liquid. Okay, so the question we are interested in is that can we have liquids that are stable inside the deep earth, for example, in the Earth's mantle? Can there be silicate melts gravitationally stable? So the first people to realize this was Ed Stoper at Caltech. So they published a paper in 1981 to show that liquids are usually more compressible than solid materials. So although at ambient condition, liquids have lower densities than typical minerals. But with increasing pressure, liquids are more compressible, so their density increases faster with pressure. So in the end, there could be a so-called density crossover. In this plot at pressures between 4 GPa to 8 GPa, you could have a density crossover between melt and mantle minerals. And if that happens, and if you have some melts in the deeper part of Earth, what happens is that the melt would, instead of going up to the surface, they would move down to the deeper part of Earth and bring all the incompatible elements to the deeper part of Earth. So in order to figure out if this is a possible scenario, we need to know basically the density of a melt and how the density of a melt changes with pressure, and of course temperature and composition. And also, there are a lot of seismic observations for the Earth's mantle, and we sometimes see so-called low velocity anomaly inside the Earth. For example, this is a study by Tauzin et al. They showed there seems to be some low velocity layer above the mantle transition zone in the deeper part of upper mantle. Okay, and how can we explain this? Can we use silicate melts to explain this, the presence of this low velocity layer? And in order to do that, we need to know the sound velocity of a liquid. But the problem is that it's very challenging to measure either density or sound velocity of liquid under high pressure conditions. Okay, for example, this is a X-ray diffraction result for a diopside crystal. As you can see, because of the periodic structure inside the crystal. You can see these sharp peaks that are related to the despacings of different sides of crystalline planes. Okay, and from this, you can actually determine the cell parameters for this crystal, and in fact, you can calculate the density of this crystal at a given pressure and temperature conditions. But this is not possible for a liquid material. And if you do X-ray diffraction, for example, for the same composition, but liquid, dioxide liquid, and all you can see are these bumps inside of these sharp peaks, okay? And from these, although it might be possible to extract some information for density, but it's very indirect and also involves large uncertainties. On top of this, liquids are very mobile and challenging to contain at high pressure. So you have to design high pressure cell very carefully. And they also highly reactive, so they can react with sample containers at high temperatures. So that makes these measurements very difficult. So previously, people first invented a technique called the sink float technique to determine the density of a silicate melt at high pressure. Okay, this was pioneered by Carl Agee and David Walker in the 1990s. Okay, they basically, if you are not very familiar with high pressure experiments, basically you have a sample like this and encapsulated by a metal.
是的呀。你昨天说那个，你说你下载的那个就下远真的是川滇的还是南北地震带的？南北地震带的。南北地震带的为什么只下远真的呢？
我是先下声音啊，好。Okay, so when you have a cell like a sample like this, you put into a high pressure cell, and this is the hydraulic press called multi-anvil you can use. And inside this multi-anvil, there are these 6 first-stage anvils that creates a cubic space. And inside this cubic space, you have these 8 tungsten carbide anvils. And in the center of these anvils, you have an octagon space. And in that space, you put a pressure medium, usually made of magnesium oxide, and you drill a hole through the MgO, and then you put your sample, and you have a heater and thermocouple for heating and temperature measurements. Okay, so at high pressure and you heat up your sample, what happens is that you can melt the sample. And inside the sample, usually we put in this sink flow technique, we put a so-called density marker. That's a solid material that has a very high melting temperature. So you put this marker inside, and if you melt the sample, if the melt is denser, the marker would float. Otherwise, it would sink. So you can conduct a series of experiments at different pressures. For example, at lower pressure, usually the solid is denser than the melt, so you have a case of sink. And if you go to higher pressure, because the melt is usually more compressible than the solid material. So eventually it will become denser than the solid, and then you get a float case. And within this region, there are cases that you can actually observe the neutral buoyancy of these density markers. So at this pressure, then you can say, okay, the melt is as dense as the solid material. And for the solid material, we can measure the density from X-ray diffraction. So you basically, you can calculate the melt density at this pressure conditions from the equation state of the solid. Okay, so we utilize this technique. We did some measurements on hydrosilicates years ago, and we combine our results and also previous results, sink float results in the literature, and we conclude that so for silicate melts, the effect of composition is very important. And it turns out, but not very surprising, that when you have more iron oxide component, okay, this is FeO, because iron is very high, has a high atomic number, so it's a denser material. So when you have more FeO components, the density of the melt increases. And if you have H2O component, the water component, then your melt decreases. So these are apparently not very surprising, consistent with our intuition. And when you add SiO2 component, because of this tetrahedral, it has some structure in the melt such that it could undergo so-called coordination change. So at low pressure, it forms the silicon oxygen tetrahedral, and at higher pressures, silicon oxygen coordination increases from 4 to 6, so it becomes a silicon oxygen octahedral. And with that, we see actually some extra compression due to the SiO2 unit. And when you have more SiO2, this effect becomes more important. And in fact, that could decrease the pressure derivative of Bach modulus of the melt. Okay, the Bach modulus is called the incompressibility of the melt. If you have a higher Bach modulus, the melt is less incompressible. So when you have a smaller K prime, it means that at higher pressure, you would expect a smaller K than the case of a higher K prime. So smaller K at high pressure means the melt is more compressible, and hence you could have higher densities when you have a silica-rich melt. Okay, feel free to ask me any questions. You can interrupt me if you have any questions. Okay, so those were the results from the sink float measurements, but there is a problem. Okay, the problem is that with sink float measurements, and for each melt, basically we could have only 1 or 2 density markers that have densities comparable to the melt. Okay, if you can't have those markers, you can't determine the melt density. So this becomes a problem because for melt, we can only have only 1 or 2 density points, and that's very difficult to determine the equilibrium state for a melt. So one way to solve this problem is to use another technique called the X-ray absorption technique. In this technique, you use some X-ray to shine through the sample, and because of for the sample, if you have a different density, it would have a different extent of X-ray absorption. Okay, so when you have, for example, a denser material compared to the surroundings, then you would see X-ray is more absorbed in this region. And in these experiments, we usually use a cylindrical sample, and then you have X-rays passing through this, and you can actually plot an X-ray absorption profile. And based on the so-called Beer-Lambert law, you can estimate, based on the intensity profile, you can estimate the density, assuming that you know the absorption coefficient, which can be determined at ambient conditions. Okay, usually these experiments are conducted at a synchrotron facility. At a synchrotron, you could have very high intensity X-ray beams, and you shine the beam through the sample, and you can have detectors. For example, there are 2 kinds of detectors used in X-ray absorption measurements. One type is called the CCD camera. You can use the camera to see the sample image, and then you can get a two-dimensional radiographic image of the sample to determine the absorption profile. Or you could have a 1D detector called an ion chamber. So for this ion chamber, when you have an X-ray passing through the chamber, ionize the gas inside this ion chamber, and you apply a high voltage across the ion chamber. So when these gas are ionized, you could have a current, and from that current you can determine the X-ray intensity. Okay, so from these you can actually determine the density of a silicate melt. And one example shown here is the study by Malfait et al. On granitic liquids. They measure the granitic liquids at different pressure and temperature conditions, and also for different water content. One of our measurements are on iron phosphide liquids, and this figure shows the X-ray image of the sample. You can see the intensity changes across the sample, and then we can determine the X-ray absorption profile and get density. The nice thing about the X-ray absorption method is that it doesn't matter if your sample is molten or in the solid form. It only depends on the density. So you can do it for either liquid or solid. And in fact, in our measurements, we see that at low temperatures, we have the Fe3P crystal, and then we can determine the density from both X-ray absorption measurement and X-ray diffraction measurement, and they gave very similar results. And at higher temperatures, and then we can use X-ray absorption to continue to determine the density of the sample. And then we see a strong, a higher thermal expansion for the liquid than the solid, and also a density jump across the melting. Okay, but still, for this method, although you can get more density points at higher pressure and temperatures, there is a problem with that. The problem is that it can only work for samples with higher X-ray absorptions. If you have a liquid that has very low density, you will not be able to see it very well. So for that, to solve that, we have developed a new technique called the X-ray computed macro tomography technique. Okay, so the motivation is that I have shown you that we studied the density for silicon melts with many compositions, and then we figure out the effect of MgO component, FeO component, and SiO2 component. Okay, but another component, the sodium oxide component, is also very important for many of the melts. For example, the basaltic melt could have some Na2O component inside, but this has a relatively low density for a sodium-rich melt, and for that, it's very challenging to use X-ray absorption technique to measure density. And also, when you have more sodium, the melts tend to have a lot of silicon component that makes the viscosity of the melt higher. And if you have a highly viscous melt, it's also very challenging to use the sink float method, because the markers will not move inside your sample. Okay, so this is an example by Sakamaki on the JDAT liquid, which is a sodium-rich melt. And as you can see, this is the sample, and that's the diamond capsule. The density contrast is, absorption contrast is very, very low. So if you use an image like this to analyze the absorption profile and to determine the density, you can imagine the uncertainty would be very large. And in fact, we have conducted first principle molecular dynamics simulations, okay, to determine the density of JDAT melt, and then we found that our simulation results are very different from their density data from Sakamaki. So to solve this discrepancy, and we actually use the X-ray tomography technique to determine the density. So in this technique, the basic idea is that this is actually similar to medical CT. So you have a sample, and then if you rotate the sample, you can take X-ray image at many different angles. And in fact, you need to do this for at least 180 degrees, and then you can get the stacked image of these X-ray image at different angles. And then you use a computer algorithm to reconstruct the image. And actually you can reconstruct the 3D X-ray image of the sample. And from that, you can directly measure the volume of the sample. And if you know the mass of the sample, and then you can use the volume to calculate density. And this was what we did for this study. So we use a device called the Paris-Edinburgh press. Okay, inside this press, we have a Paris-Edinburgh cell, and this is our sample. And across this cell, there is low absorption material for X-ray. So we can see through the sample cell and to directly image our sample. And inside this pressure cell, we can actually rotate the sample for 180 degrees. In fact, we can do 360 degrees, but 180 is good enough. So we do this rotation under high pressure and high temperature conditions. And the key here is that because we have a molten sample, we need a sample capsule to contain the sample. So this, and also we need to have some absorption contrast between the capsule and the sample. So we had to use some metal capsule to contain the sample. But the problem is that for typical metal materials, for example, people like to use gold or platinum, they have very high absorption. So in this case, you will not be able to see through the sample capsule. And of course, then you cannot get a tomography image. So in this case, we have chosen the molybdenum capsule, which has relatively high absorption, so that we have an absorption contrast with sample, but relatively low absorption such that the X-ray can penetrate through the capsule and we can still image the sample. So after doing this, we can actually get the three-dimensional image of the sample, and we can do some calculation to integrate the voxels and to get the volume. Okay, these are our results on JDAT liquid, and shown as this black symbols. And you can see that our results are quite consistent with our previous first principle calculations shown by these squares. Okay, the blue curve is the result from Sakamaki from the X-ray absorption measurements. And as you can see, our experimental results agree well with our simulation results. And it's very surprising result that the density of a sodium-rich melt can increase with pressure very fast. Actually, if you compare the density of jadeite melt shown by this red curve with the density of other silicate melts shown as these dashed lines, you can see that the density of jadeite, although it's small at low pressure, but becomes higher very quickly at high pressure. And this was quite surprising. It turned out when you add sodium component, it can significantly reduce both the Bach modulus and the pressure derivative of Bach modulus. And you can make the melt very compressible even at high pressures. So eventually, this sodium-rich melt could become denser than the upper mantle as shown by this prime model. Okay, but there's still a problem. This is nice, but still, if you look at the fitting of the equation state, we found that there is a large trade-off between the Bach modulus and its pressure derivative. So this figure shows the correlation between K and K prime determined from our experimental data. And this was the red dot is the optimized solution. And you can see that there is a very strong correlation. This is the 1 sigma envelope, and you can see there are a lot of combinations of K and K prime could explain our experimental data. And in fact, this was discovered by Beijing and Walker in 1993 in their experiments too. They can't determine actually the K prime of their result, their sample. Okay, so how do we solve this problem? And the solution is that we can use the ultrasonic technique to measure the sound velocity of the sample. And from the sound velocity, we can actually directly calculate the Bach modulus and K prime from those measurements. So how do we do this? This basically is to simulate earthquakes inside the lab. And we have the multi-anvil, and then we attach a piezoelectric transducer on one of the tungsten carbide anvils. So for this transducer, if you apply a voltage, it creates some strain, and that if you have a periodic wave, for example, a sine wave, then you have a vibration of the transducer, then that creates elastic waves inside the sample. And just like real reflection seismology, you could have seismic elastic waves reflected at different interfaces inside the sample cell and received by the transducer, again, converted back to electric signals and received by the oscilloscope. So these are the typical signals, ultrasonic signals we see in the oscilloscope. And these, for each of these echoes, they are reflections at different interfaces. So the echoes we are interested in are the one echo reflected in front of the sample, and one echo reflected at the back of the sample. And you can determine the travel time between these two echoes. And that is the travel time for the round trip of elastic waves through the sample. Okay, so if we know the travel time, next we need to know the sample length in order to determine the velocity in the sample. And for that, we can again use a synchrotron, and we do these experiments at the APS 13 IDD beamline, and we have a high intensity X-ray. We can convert the X-ray to visible light and then received by a CCD camera. We can see the sample image, just like medical imaging. And then you can directly measure the sample length, and then you can get the velocities. But it's easy, relatively easy for solid materials, but not that easy for liquids. There are a couple of challenges. So the first is that we need to find a capsule material that can confine the liquid at high pressure, but does not react with the liquid. And also we need to have materials in front and back at the back of the liquid that creates enough acoustic impedance contrast so that we could see the liquid from the elastic waves. And also we need to have X-ray contrast, absorption contrast between these materials with the sample, such that we could see it from the X-ray images. Okay, so for different materials, we actually need different combination of these backing materials and capsuling materials. For example, for iron-rich liquid, because iron has a relatively high absorption, so we use low absorption materials like alumina in front and at the back of the sample. And there are also strong materials that has high impedance contrast with the liquid. For silicate liquids, because when you have silicate liquid, it has relatively similar X-ray absorption with the alumina. So you can't use alumina on the side. You have to use metal instead. So we use a molybdenum in the front and at the back of the sample, and also at the side to contain the silicate liquid. So here shows one example that we measure the sound velocity of a dioxide liquid at high pressure. And we started with a glass dioxide starting material. At temperatures about 1000 Kelvin, you can see the signals for a glass sample. Okay, this is the signal at the front of the sample. This is at the back. So this gives you the travel time for the waves travel through the sample. And this is for the glass sample. It has a relatively high velocity. And when you increase the temperature, at some point, you actually observe that a change from a glass sample to a crystalline sample. This is the recrystallization of the glass. And what happens is that the travel time becomes shorter than for the glass sample. So you have a higher velocity. And if you continue to increase temperature, and eventually you enter into this partial melt regime. In this partial melt regime, you could have a basically layered structure because of the temperature gradient inside the cell. So you could have, on one side, you have the remaining solid, and on the other side, you have relatively higher temperature, so you could have a melt. A partial melt. So in terms of ultrasonic signals, you also see two signals. One is the signal reflected by this solid melt boundary. Okay, and then another signal reflected at the back of the liquid part. So you get a split of this sample signals into two signals. And then if you continue increase temperature, eventually this interface between solid and melt disappear, and you can have a completely molten sample, and then you have the signal for the liquid. And in this case, you see that the velocity is much lower than velocities in the solid and the glass, and you can see that the travel time becomes longer. Okay, so these are our results shown as these black symbols. These are for the velocity of dioxide liquid, which increases with pressure, of course. And this purple symbol is the measurement at ambient conditions from eye and line. These are the results for dioxide glass, and the green ones are the results for dioxide crystals. As you can see, the melts have much lower velocities than glass and crystals. Okay, and then if we know one density point along this curve, for example, if we know the ambient melt density, we can actually integrate this curve to get the density as a function of pressure. Okay, this is the result we got for dioxide liquid at high pressure, and then compared with the density measurements from other techniques. These red symbols are from the shock wave technique. The blue line is from our results. And as you can see from the Bach modulus and K prime correlation, you can see that with ultrasonic technique, we can much better constrain K and K prime better than the density measurements. Okay, I think I'm gonna, because of time, I'm gonna skip this part. Basically, I want to show you that you can't use glass velocities as analogs for liquid velocities. You have to measure the velocity of liquid itself. I'll skip this part. To summarize, for the experimental part, basically we have these 4 different techniques, and for each different technique, it has its own pros and cons, and we need to combine these techniques actually to determine the density and sound velocity of melts. Okay, so next I'm gonna talk about the carbon-related melting in the Earth's upper mantle. As we know that the carbon is cycling through the surface layers and the deep layers of Earth. Okay, this is a summary by Bob Werner to show the cycling of carbon. Of course, in the atmosphere, we have carbon dioxide, and in the deeper mantle, we could have carbonates and either graphite or diamond. Okay, it turns out more than 19% of carbon is actually inside the deeper interior of Earth, and probably more than 50% inside the Earth's core. But there should be a lot of carbon inside the Earth's mantle, and they could have different forms. For example, a shallower part of Earth's mantle, they are probably in the carbonates form because of the relatively high oxygen fugacity, and in the deeper part, they could be in the more reduced form, for example, in terms of graphite or diamond, or even maybe the iron carbide. Okay, so the motivation is that inside the upper mantle, carbon has very low solubility in mantle minerals. For example, for typical minerals, you cannot accommodate a lot of carbon. So carbon should be either in the form of graphite or should be in the form of carbonates. And in the upper mantle, because of oxygen fugacity, it should be in terms of carbonates. But if you measure the melting temperature of these carbonates, it turns out they have very low melting temperature compared to the mantle solids. So this makes us to think that if you have some carbonates inside the upper mantle, they should be in the liquid form. And it turned out, as shown by this study, Thompson et al., they showed that at relatively low pressure, if you have some carbonates, they could become some carbonated silicate melts. And if you go to the deeper part, they could become even, you could even have more carbon in the melt to make a carbonate melt. And here I want to distinguish these 3 terms. Okay, if you have, say, a lot of CO2 component in your melt, then the SiO2 component, you would say the melt is a carbonate melt. And if you have more SiO2 than the CO2 component, then you would say it's carbonated silicate melt. Now, sometimes I choose to use carbonate melt. This is for the pure carbonate system. For example, if I have a magnesium carbonate, and then I melt it, and I could get the pure carbonate melt. And here, when we do experiments, we study pure carbonate melts, but when we talk about applications, we meant to say carbonate-rich melt or carbonated silicon melt. Okay, so because of the redox situation inside the Earth, when you have carbonates enter into the deeper part of Earth, you could have melting of carbonates in the upper mantle, but when they enter deeper and deeper, and because of the redox reaction, they could get reduced to the diamond form and becomes back to solid. So this is called the redox freezing, and you could have diamonds in the deeper part and recycled through the mantle convection, and under beneath the mid-ocean ridges, you could have mantle upwellings, and they got oxidized again and to cause melting in these regions. This is called redox melting. Okay, there seems to be some geochemical evidence for the presence of carbonate melts in the Earth's mantle. For example, this is a work by Li et al. On the magnesium isotope, and they show that there is some magnesium isotope anomalies in the eastern part of Asia, and then they explain this magnesium isotope anomalies based on the presence of carbonated silicate melts. So suggesting there might be some carbonate melts in the deeper part. This is a study by Zhang et al. And they found that there seems to be evidence of carbonate-rich melt beneath the South China Sea, and they found that there is this ancient mid-ocean ridge that stopped spreading, but in these samples they found some CO2 components, and they explain this by the formation of carbonated silicate melts in the deeper part, and the evolution of this carbonated silicate melts through the depth. Okay, so the question we want to explain is, we want to ask is that can we see this from seismic observations? Can we directly observe any carbonate-rich melts in the Earth's upper mantle? And for that, again, we need to know the density and sound velocity of carbonate melts. But these are not easy to determine. For example, at ambient conditions, these carbonate melts would decompose before melting. So under these conditions, you can't actually make a carbonate melt like a calcite melt or a magnesite melt. That's impossible to do. So what people did was that they put many components together. For example, Liu and Lan and Hurt and Lan, they study a complicated system with calcium carbonate, lithium carbonate, sodium and potassium carbonate all together to determine the density of the melt. And then they try to figure out the partial molar volume of calcium carbonate. But this is a very direct technique to determine the density of these melts. And also O'Leary et al., they studied the ultrasonic sound velocity of these complicated carbonate melts, but no direct measurements on calcium carbonates and magnesium carbonates. Okay. Another problem is that carbonate melts have relatively low densities, so the X-ray absorption is also very low. So it's very challenging to determine the density of carbonate melts. There was one study by Dobson. They used falling sphere method to determine density, but this has very large uncertainty, up to 20%. And there's some study to use fusion curve analysis to determine the equilibrium state, but this was only applied to the potassium carbonate because you need a lot of thermodynamic parameters. Okay, but we don't know the parameters for these melts. And there's no sound velocity data exist at all for the carbonate melts. So in this study, first we use previous technique we introduced to determine the ultrasonic sound velocity for a dolomite melt, which is calcium, magnesium carbonates. This is the composition believed to be present in the Earth's upper mantle. And for this melt, we again designed some special capsuling material and backing material. For example, we use alumina on the side, but because alumina, in terms of X-ray absorption, is very close to calcium, to the carbonates, so we had to use some material as a denser material as the capsule to indicate the sample length. So we use a platinum capsule in this case. But the nice thing is that we can see the sample length, although we can't really see the sample X-ray, but that doesn't matter because for melt, we don't care about the X-ray diffraction. So from this, we can again measure the ultrasonic signals. Similar to before, we could see the signals for the sample, for the partial melt, and for the liquid. And from that, we can measure the velocity for the dolomite melt as a function of pressure and temperature. And from these results, we see that for dolomite liquid compared to silicate liquid, it has a slightly lower velocity than the dioxide liquid, but at higher pressures, it has a steeper slope. So it increases faster, and at higher pressure in the upper mantle, the dolomite melt has a higher velocity than the dioxide liquid. Okay, these are we also performed the first principle molecular dynamics simulations using either the LDA and GGA assumptions, and we found that the LDA assumption produced better velocity results, or more consistent with our experimental results. And for the density part, as I said, it's challenging to use X-ray absorption technique. So we use the sink float technique. And here we use a density marker called the boron carbide, B4C. And this does not react with the carbonate much, but has a density comparable to the carbonate melts. And we were able to obtain the float case and the neutral buoyancy case, but we failed to obtain the sink case because at much lower pressure, the melt decompose and we can't determine the density. So from this neutral buoyancy data point, we actually can determine the density of dolomite melt. We can actually integrate our velocity result to get the equilibrium state, which is the density as a function of pressure. And compared to the simulation results, we found that it lies between the LDA and GGA assumptions. The slopes are consistent. Okay, so this gives us an indication that it's very difficult to use first principle calculations because you don't know which assumption would work. And in fact, they gave us quite large range in terms of density. So we had to use some experiments to determine the density. And combining the sink float results and the sound velocity results, we actually can determine the K and K prime for the liquid very well. These are very tightly constrained. Okay, this is pretty much my last slide. Based on these results, we can actually calculate the velocities of partial melt in the Earth's upper mantle. But because of the melt fraction is very, very low, when you calculate the velocities, the velocity decrease is very small, and it would be comparable, still be comparable to the velocity of the prime. So you can't really use the velocity anomalies to determine the melt fraction. So here we actually compare the VP-VS ratio as an indicator to show the presence of a melt, because VS is more sensitive to the presence of melt. For the melt, VS is 0. So when you have a little bit melt, VS decrease a lot, so you could have an increase of VP-VS ratio. So here we compare our calculated velocities for the Earth's upper mantle with the presence of a certain melt fraction. For example, the black curve is for the case without any melt, and then the blue one is for 0.05% of melt. And then you compare these VP-VS ratios with the results given by the prime model or other seismic models, and we can see 3 different regions. In this region, we see that we need to have some melt to explain the result, and this corresponds to the low velocity zone beneath in the shallow part of our upper mantle. Okay, and then there is this region. We found that between 180 kilometer depth to 330 kilometer depth, in this region there seems to be some melt to present. However, you can't really use silicon melts to explain the presence of this to explain this VP-VS anomaly, because when the temperature to melt a silicon melt is very high. It's actually higher than the mantle solidus at this depth. So you have to have some carbonate melt in order to explain this result. So by doing this, we found that we need about 0.05% of carbonate melt to explain this seismic result, and that amounts to about 80 to 140 ppm by weight of carbonates, and that is actually consistent with geochemical estimates. Okay, that's my last slide. Thank you.
Okay, thank you very much for giving the talk. And now it's time for questions. 大家也可以用中文提问 or you could type your question in the chat. When you ask a question, please let us know your name and your institution. Okay, I have a quick comment, sort of discussion, I say. So in this figure, so between 200 and 300 kilometers, the initial carbonate rich melts. So to me, that's like the minimum amount of carbon in Earth's mantle, because carbon, if it is in other forms, then they create a different VP and VS ratio that might not be covered by this box that should be your plot. So I would say that this 80 to, I say 140 ppm of carbon in the form of carbonate melt is the minimum for the depth in the deep or the deep upper mantle. But I have a relevant question to this is that do you extend this to the region above the 410? Because for 410, low velocity zone, people have been talking about are related to the dehydration from the mantle transition zone. So I don't know whether this model extends to the deeper depth, or how do you view this problem or this topic?
We never tried, but that's a very nice suggestion. That it would be very interesting to compare for the deeper part of Earth to see if there is any anomalies. And regarding to the concentration, I agree this could be a lower limit. Actually, this is I think this is a very crude study that we actually make a lot of assumptions. For example, the upper mantle could be very heterogeneous. This comparison is for the global result, but you could have regions that are rich in carbonates, and there are regions that have lower oxygen few gases. You could have other forms of carbon, so that could result differently. And we have to assume that the seismic velocities does not change with the carbon content very non-linearly, such that we can make this average. Otherwise, we have to use local VP-VS ratios for this comparison. Such are rare because when you make seismic observations, VP and VS, the P waves and S waves travel through different paths. So it's very challenging to get VP and VS ratio for a certain area. But it would certainly help if there are more observations.
Okay, more questions from the audience?
老师您好，我是那个浙江大学博一的学生，我叫秦奔。然后我想问一下，就是请教一下您之前提到的，就是这个碳酸镁在就是melt 之前就已经就是反应了是吗？还是？
对，就是说在常压下，你如果加热碳酸镁和碳酸钙的话，它们会先分解，就分解成氧化镁加二氧化碳。而不是先熔。在高压下呢，它可以先熔，然后你要继续加温，它有可能会分解。所以就是说它这个分解反应的这个温度和这个熔的这个温度，你要看谁高谁低。
好的。
所以呢，在常压下的话，这些实验都没有办法做，因为它会直接分解，所以人们就把这个碳酸钙、碳酸镁和其他的这些碳酸钠、碳酸钾混到一起啊，那些常压下是可以熔掉的啊，混到一起然后来测，但是你这样的话，你是没有办法知道它这个比较纯的项是什么样的性质。
好的，明白，谢谢您。
Okay, I think that's so much for today's seminar, and thanks again for Dr. Zhicheng for giving this great talk, and thanks everybody for participating. Okay, have a good day.
Okay, thank you. Have a good day.